In this episode, the world's tallest freestanding tower.
It's a striking landmark, the world #1 tower.
Taking structural design to new heights.
The number of the steel was about 37,000 in total.
And the innovative pioneers of the past.
This is unbelievable. This rocket is just so big.
When I try to wiggle it side to side, I really can't.
That made the impossible possible. Tokyo, home to over 35 million people. With vast suburbs stretching 14,000 square miles, its low-rise sprawl is a direct result of a serious construction challenge, one of nature's most deadly forces: earthquakes. But as space in the city runs out, engineers are, for the first time, being forced to look up. This evolving skyline poses a new problem, one that, having lived and worked here, high-rise architect David Malott is well aware of. The city's 333-meter communications hub, Tokyo Tower, is being neutralized.
You can almost see it's going to be blocked out by a building. So Tokyo Tower is no longer serving its purpose as a television transmission tower. The signal is being blocked.
In a nation that experiences 1,500 earthquakes a year, uninterrupted TV and radio communication is vital. A problem that requires a radical solution.
Here it is, Tokyo Skytree.
The Tokyo Skytree is the world's tallest freestanding tower, and a project the like of which has never been attempted before in Japan.
At 634 meters tall, it's double the height of Tokyo Tower. It's got the most advanced engineering and technology we have available today. This is the solution for Tokyo's connectivity.
Completed in 2012. The sheer scale of this engineering marvel offered a career-defining opportunity for designer Tetsuya Tsuchiya.
I think all the architects and engineers have some dream to create, something high and something, going to the sky.
Its record-breaking proportions demanded extraordinary solutions from structural engineer Atsuo Konishi.
This is the first time to design the 600-meter high-rise towers in Japan. We have to solve the many problems.
The 634-meter structure is more than 4 times the height of the Great Pyramid of Giza. Its spine is a 375-meter hollow concrete core, cloaked in a 37,000-piece steel frame, which morphs from a triangle to a circle. It has 2 observation decks. The tallest at 450 meters is one of the highest in the world, and is topped by the state-of-the-art antenna tower, capable of transmitting 100 kilometers away. Construction begins in 2008, but before Skytree can even rise out of the ground, its designers face a seemingly impossible problem.
Where we are now used to be part of Tokyo Bay. The land I'm walking on was underwater. So what that means is the soil around here is extremely soft. And for engineers, this presents a big challenge, especially when you do something of that height in a place that has earthquakes and typhoons. It's going to want to push the building, so that building needs to be firmly anchored into the ground. Now, if you don't get the foundations right, then that's a recipe for disaster.
And with the tower exerting 67,000 tons of force, how do you ensure such a colossal structure will remain standing on such unstable soil in a seismic zone? It's a challenge that may not have been possible without the great innovators from the past. It might be far from perfect, but soft ground has never put off history's builders.
Oh, forget it.
Ole!
In fact, some of the world's most famous cities
Na zdrowie.
have been built on swamps and marshes.
Bravo. Oi, I'm getting wet.
In New Orleans, the ground is so soggy they famously had to build their cemeteries above ground.
Ah, that's better.
And Berlin is crisscrossed by a constantly changing 40-mile network of pink pipes used to pump the ground free of water.
Ah, wunderbar.
Architectural historian Jen Mason-Garb has travelled to one of California's most iconic coastal locations to discover how a change of fortune sparked an engineering revolution.
It's hard to imagine, but San Francisco hasn't always been this big. At the beginning of the 19th century, it was a small outpost on the western edge of the United States. All of that changed in 1848 when prospectors struck gold.
As the population swelled, by the 1890s, the city's infrastructure was creaking under the strain.
One of the areas that needed a lot of attention was the old ferry house that sat here in the harbor.
The solution for San Francisco's booming Bay Area would be completed in 1898, the monumental new ferry building.
Wow, what a great building. It's got that great tower and all these bays lined up along the water. It's so much bigger than its original predecessor. It weighs about 150 million pounds, which translates to about 75,000 tons.
But building this structure was an unprecedented challenge. The massive weight, including the 75-meter tower, sits on 55 meters of bay mud, which, being in a seismic zone, creates near impossible building conditions.
So those tasked with designing a new ferry building really had to think about innovative solutions in order for the building to be successful.
Supporting architect Arthur Page Brown's grand design was down to engineer Howard Holmes. He proposed a huge concrete slab set on piles driven into the ground. But traditional methods simply wouldn't be enough.
I've got some wet sand, which is the same kind of sand that's here underneath the ocean. And this wooden plank is to help us see that concrete mat that the entire building is sitting on. And these nails are those wooden piles that are driven down to the sand. In a typical building, you might use only as many piles as you would need to support the building. So let's see if that works. I can put quite a bit of load on this, but we're in a seismic zone. You can see that I can turn this sideways pretty easily. So wiggle, wiggle, wiggle.
To survive earthquakes, Brown's Ferry building would need something special.
So here's my new demonstration with lots of piles. If I take this last one, hammer this guy in, and try it again, let's see what happens this time. Wow, not only can I not push it in very much, but when I try to wiggle it side to side, I really can't.
And the secret of this stability is down to friction.
Friction is created around the surface area of each of these piles. And more piles equals more surface area. And because it's much more stable like this, any earthquake load, all of those forces are just going to be absorbed by all the piles, making the rest of the building much more secure. Brilliant.
Over 5,000 wooden piles were driven deep into San Francisco's semi-fluid sandy mud, each cluster supporting just one of the structure's 111 concrete piers.
It's a foundation with 3 parts, which you can see here. a reinforced concrete mat under the whole building, then concrete piers, then wooden pilings driven down to the mud. Those wooden pilings are about 80 feet in length. Underneath the tower, there are 345 piles alone.
On its completion in 1898, the new ferry building had the largest foundations for a structure over water anywhere. And to this day, it continues to defy sinking sand and anything that nature can throw at it.
This design has withstood the earthquakes of 1906 and 1989, both of which caused massive damage throughout San Francisco. The building has proven itself through its innovative engineering.
At the 634-meter Tokyo Skytree, engineers take Howard Holmes' method into the 21st century. 131 concrete piles are driven into the soft ground to stabilize it. But the building's record-breaking height adds a further problem.
When the big forces apply to the tower, like a typhoon or big earthquake, the entire tower acts like a giant lever and put enormous force on its base, pushing up one side and pulling up the other.
To overcome this, Skytree needs a unique system. Its 67,000 tons of force is exerted onto a tripod-shaped base.
Right now I'm standing at one of the feet of the tripod structure, and underneath this here is a bunch of wall foundations.
"50 meters below the surface, 3 clusters of 1.2-meter thick walls use friction with the surrounding soil to increase horizontal rigidity. Connecting each cluster are 3 50-meter wall piles, with added knuckles acting as spikes, further increasing friction. Combined with the column piles, the tower's foundations act as a tree's roots, stabilizing the superstructure in the most extreme of conditions.
It has a huge surface area, and the friction between the wall and the ground soil acts as an anchor. And constructing it, a huge amount of it was enormous work. This is a very special foundation system, exclusively used for the Tokyo Skytree.
But to complete the world's tallest freestanding tower, engineers face more challenges and have to turn to another of history's great innovations.
It's a brilliantly simple solution and sparked a renaissance in skyscraper construction.
To produce more impossible engineering. In Tokyo, Japan, the 634-meter broadcast tower Skytree pushes high-rise construction to a whole new level. And its engineers to their limits.
It is the world's tallest tower in one of the world's busiest cities. So it was very challenging work for us to construct.
More than 6 times higher than London's Big Ben and twice the height of its predecessor, the Tokyo Tower, Skytree changes the face of Japan's capital. High-rise architect David Malott appreciates building higher than ever before in the capital is a huge challenge, particularly when land is running out.
The engineers at Tokyo Skytree had to put a tower that's twice as high as Tokyo Tower on a piece of land that's only a quarter of that size.
The proportions of a super tall tower are crucial. If a structure is more than 5 times higher than its narrowest base dimension, it can become unstable in the wind. Skytree's ratio is a staggering 9:1.
It's one thing to build tall and wide, and it's a much more challenging thing to build tall and slender.
So, how do you build a super slim, record-breaking tower on such a confined plot? Engineers have always been able to build short and fat. And after a while, they mastered tall and fat. But building tall and thin has often been a problem.
Are you sure? Go for it.
Ireland's highest round tower is an amazing feat,
I told you, perfect.
but isn't exactly straight. The first St. Mark's Campanile in Venice certainly looked the part.
Mamma mia.
But the impact of the weather and the weight of its 5 mighty bells led to disaster.
We're going to need a newer tower.
Engineers needed to think again. During the 1920s, Chicago became synonymous with skyscrapers. By the 60s, with space increasingly at a premium, developers wanted to build even higher. But traditional, bulky construction methods were stifling their ambition. In 1968, engineer Fazla Khan came up with a game-changing solution.
All right, thanks.
Local architect Jayshree Shah has come to see for herself.
This is the groundbreaking building that Khan was working on.
The 344-meter Hancock Center was the first of Chicago's towers to reach 100 floors. Despite its impressive height, it sits on a footprint 27% smaller than the city's second tallest skyscraper from that time, the Chase Tower.
So this is the very top of the Hancock Center. What an incredible view.
So, how does the Hancock Center stand up to the Windy City's challenging environment?
So now I'm going to show you how this works. Just take a look at this skyscraper-shaped tower. If I push on it just a little bit, like a lateral force similar to the wind, you can see how much it bends. Now if I push even more, you can see how it begins to twist. Oh, jeez. All right, I broke it.
But the simple addition of 45-degree cross braces changes everything.
You can see how much stiffer it is. When I push against the building now, it's not bending or twisting as it did before.
Khan's use of braced tubing reduced the horizontal loads on the building. As the winds pushed against the elevations, they now transferred down the diagonals to the base of the structure, easing the loading on the building's vertical members.
It's a brilliantly simple solution. Fazla Khan's brace tube design sparked a renaissance in skyscraper construction.
Engineers at Tokyo Skytree have drawn on Fazla Khan's genius bracing, creating a record-breaking super slim structure that dwarfs all around it.
Steel bracing structure is very important to stabilize this tall and thin structure.
In an area renowned for typhoons, building a tower almost double the height of the Hancock Center on a footprint 51% smaller is a mind-blowing feat. Engineer Hiroshi Takagi is standing in the stunning solution.
The number of the steel was about 37,000 in total. As you can see, the piece of the steel is huge, and the biggest one is 2.3 meters in diameter.
The 37,000-piece steel framework consists of 3 layers with thousands of triangular trusses. Immensely strong, it can resist wind gusts approaching 250 miles per hour.
This outer steel frame carries all the weight against the strong wind. You can also see through it, so that the wind can pass through the tower so that we can reduce the wind load.
In building the world's tallest freestanding tower, its engineers have achieved proportions that many thought were impossible.
If you look at the Eiffel Tower, the height is about 320 meters. The stance is 120 meters. So it's almost like, 1, 2, 3. But this one, the height is 9 times taller than the width of this tower.
As well as defying the odds, its designers have also created a shape that makes Skytree totally unique.
The shape of this tower is characterized by the triangular shape at the foot and gradually transformed into circular shape to the top. That came from traditional Japanese architecture, so gentle curve. This is a very beautiful structure, straight into the sky. It's an amazing structure.
But to complete this engineering marvel, Skytree's team face another huge challenge and will have to turn to a truly innovative solution from the past.
It was a beautifully simple concept that ultimately helped push our exploration out into space.
To produce more impossible engineering. In Tokyo, architect Tetsuya Tsuchiya, engineer Hiroshi Takagi, and a huge construction team are transforming the city skyline. At 634 meters, the Tokyo Skytree is the world's tallest freestanding tower, and an engineering challenge never before attempted in Japan.
People can see this tower, and also we can see the city. So I think it's a really great viewpoint to really understand the city of Tokyo.
Building to such heights is an incredible achievement anywhere. But as high-rise architect David Malott is aware, building to this scale here means conquering a seemingly impossible problem.
Japan is part of what we call the Ring of Fire. So it's one of the most active seismic zones in the world. So earthquakes are a part of daily life here in Tokyo.
This is a very tough condition for the high-rise building in Japan.
It's a very big challenge for us to control the swaying and the movement of this tower.
So the engineers of Skytree were tasked to build not only the world's tallest television tower, they had to put it in what is probably the world's most dangerous location.
In a country that is subjected to around 1,500 earthquakes a year, how do you ensure a super tall tower will remain standing? The solution would come from an unlikely source and a truly remarkable innovation from the past.
Launch commit, liftoff. We have liftoff.
Space historian Amy Shearer Title is in Florida, at the home of one of history's most awe-inspiring projects, where everything is extreme. From one of the world's largest vehicle assembly buildings,
This is unbelievable. This is really incredible.
to rockets of unprecedented power.
This rocket is just so big. It's so great.
From the 60s, Kennedy Space Center was the launch pad for NASA's epic Apollo space missions.
This is really amazing to be standing here. This is launch pad 39B. This is where the Apollo 10 crew launched and went all the way to the moon to orbit before coming home. At the moment of launch, the 5 F1 engines together produced more power than 85 Hoover dams. The sound of the launch was so intense, they actually had to dump 3 million liters of water onto the pad every minute just to dampen the sound waves so they couldn't bounce back up and rip the rocket apart.
Just like old times, it's beautiful out there.
Achieving such an explosive liftoff called for a lot of energy. Almost 2 million litres of rocket propellant was needed to get the 110-metre rocket off the ground.
Delivering all that fuel to the rocket required umbilicals, masses of cords and wires running all the way up the service structure.
Attached to the rocket by spring-loaded swing arms, it was essential the umbilicals remained in place until the very last second, before an electrical discharge jerked them and the swing arms back towards the launch tower.
However, the challenge was controlling the swing arms' sudden, powerful movements. They had to make sure they wouldn't break off from overexertion or bounce back and hit the rocket as it left the launch pad. Thankfully, there was one engineer working on a solution.
Former Air Force engineer Paul Taylor was working alongside NASA, developing new technologies for the space program. His patent for an innovative shock absorber design would offer the breakthrough for the Apollo mission's critical launch procedure.
The concept Taylor came up with was the fluid damper or the liquid spring, and it works something like this. Now imagine that this coffee press is our fluid damper, and it's sitting between the tower and the rocket. You can see that when our damper is empty, it offers very little resistance to weight, or the force of the swing arm when it's released. But if you fill it full of fluid, look at the magic of the green liquid. And if you put the weight back on, you can see it compresses much more slowly. So what's happening is, as the plunger is pressed, the liquid is forced through the holes. This creates resistance, which dissipates the energy, which makes the plunger move more slowly.
During a launch, as the umbilical-laden swing arm springs back, the attached fluid dampers are compressed and the fluid inside forced through holes in the piston, creating friction, slowing the arm to 0 speed at the end of travel and minimizing risk of damage to the tower or rocket. In 1969, Taylor's ingenious system proved its worth, as Apollo 10 safely launched on its pioneering mission to orbit the moon, making its mark in space travel history.
We are go for a mission to the moon at this time. We have ignition sequence start. All engines running. Launch commit. Liftoff.
His hydraulic innovation has stood the test of time and is still in use today, protecting sensitive equipment during launches to the International Space Station.
It was a beautifully simple concept that ultimately helped push our exploration out into space.
In Tokyo, Skytree engineer Atsuo Konishi and his team face a potentially devastating natural phenomenon.
In Tokyo area, the big earthquake occurred. That is a challenge for us to design such a high-rise structure.
Their solution to controlling the shake of the tower is centered around the earthquake-proof ancient Japanese pagoda. Its tiered wooden structure traditionally stabilized by a shimbashira, a flexible quake-dampening central pole. Skytree's engineers emulate this ancient technology, creating an enormous 375-meter concrete column set on 6 giant rubber bearings.
Now we are here at the bottom of the core column. I came up with the core column system because there is a Shimbashira in Japan.
And sandwiched between this mass and the tower's steel structure lies the Apollo-inspired fluid dampers.
The upper half of the core column is connected with the oil damper to the steel structure.
Situated between 125 and 375 meters, the series of fluid dampers control the movement of the freestanding 10,000-ton concrete core and the steel exoskeleton throughout a seismic event.
During the earthquake, the core column designed to shake just a little bit slower compared with steel towers. That condition is a reason why the core column system reduced the vibration of the Tokyo Skytree.
The different vibration cycles of the central column and the steel frame can counteract the vibration of the entire tower.
If the oil damper isn't installed, the core column will collide the steel structure. The core column will collapse.
The system is so effective, it reduces an earthquake's vibration by 50%, meaning Skytree will survive Tokyo's most severe seismic activity, the like of which is only expected once every 1,000 years.
The vibration control system is a unique system for Tokyo Skytree. This is the first one in the world.
But as well as standing firm during a magnitude 7 quake, this state-of-the-art communications hub also has to continue to transmit. And to do this, the vibration of the 140-meter antenna tower has to be controlled with pinpoint accuracy.
The swaying of the antenna has a really bad effect if you really want to enjoy the TV show. The movement of broadcasting tower is allowed only a few centimeters, so we have to control the swaying.
The solution is a secondary vibration system, an almighty piece of engineering perched at the pinnacle of the tower.
To control the swaying and the movement, we have tuned mass damper buried at the top on the antennas.
The tuned mass damper contains a 40-ton concrete block, which moves like a pendulum. During an earthquake, there is a time lag between the vibration of the tower itself and the movement of this concrete mass, cancelling out the vibration of the main structure, resulting in a super stable antenna system that can transmit in Tokyo's most extreme seismic activity.
Without this system, our broadcasting cannot continue after the big earthquake.
Brilliant engineering has tamed one of nature's most devastating forces. But to complete this mammoth super tower, its designers face more challenges and have to draw on another great innovation from the past to produce more impossible engineering. Completed in 2012, Tokyo Skytree has set a new benchmark in high-rise design. Acting as a communications hub, the 634-meter tower can transmit up to 100 kilometers away. But for its architect Tetsuo Tsuchiya, this engineering colossus stands for much more.
The Skytree has two major functions. One is, of course, this is a broadcasting tower. And at the same time, this is a very interesting observation tower for the tourist. So getting here and enjoy the view is the most important thing in this tower.
Having designed some of the world's most iconic super towers, David Malott can appreciate that creating a bird's eye view from one of the world's highest skywalk posed tremendous problems for Skytree's team.
When you're building observation decks at heights of 350 meters, 450 meters, it's going to be subjected to tremendous force from typhoon.
The wind speed here up above is maybe 50% stronger than the ground level. And it was very important that any guests feel safe during their visit, even in bad weather or any earthquakes.
So the engineers need to come up with materials that can withstand whatever Mother Nature wants to throw at it.
And to offer the perfect view, one material is crucial. But how do you guarantee that glass will remain in a safe state in the face of some of the planet's most extreme weather? Achieving this would have been impossible without a chance discovery in France's congested capital over 100 years ago. Scientist Suzy Shi is in Paris to discover how the city's notoriously bad traffic inspired a discovery that would transform safety in the modern world.
In 1903, driving was fast becoming the hot new hobby among Parisians. But like today, the traffic was congested and dangerous, and accidents were commonplace.
The situation was so concerning, one local paper ran a feature on the spate of recent crashes.
When the article in question came to the attention of one native Parisian called Edouard Benedictus, it sparked an idea that would go on to change the world.
Born in 1878, scientist Edouard Benedictus studied chemistry in Germany before setting up a laboratory in Paris. It was here that his inspired breakthrough happened, courtesy of the capital's traffic nightmare.
The newspaper article outlined how car windscreens were causing drivers serious injuries in the case of an accident. The windscreen would smash into shards, which in some cases proved fatal.
Incredibly, a solution to this concerning problem had already been discovered by Benedictus, entirely by chance.
During some routine testing at his lab one day, Benedictus accidentally knocked a glass flask off a shelf. And remarkably, instead of smashing into 1,000 different pieces, it actually maintained its shape.
Examining the shattered flask that had mysteriously remained in one piece, Benedictus observed remnants of a liquid plastic within the vessel and concluded that its thin coating had held the broken glass together.
Just days later, inspired by the article about the dangers of driving, Benedictus had a brainwave. He realised that this plastic-coated glass had the potential to save lives. So this is a piece of laminated glass, and it's like the modern evolution of Benedictus's discovery. It's basically just two pieces of glass which are bonded together with a piece of plastic between, which holds it together. And over here, I also have some pieces of just normal sheet glass. And this is similar to the glass that would have been used in a car windscreen in Benedictus's time.
To see how each one reacts under impact, a 2-kilogram steel ball is set 4 meters off the ground. First up, the normal sheet glass.
Ready to go. Oh, wow, okay. So this piece of glass is really smashed. You can imagine how dangerous one of those sharp shards of glass would be if it came flying at your face during a car accident. So instead, let's try a piece of laminated glass and see what happens. All right, place my laminated glass now. But this time, I'm going to raise it up higher.
To prove the strength of the safety glass, this time the drop height is raised to 6 meters.
it didn't go through. Oh, wow. Okay, so my steel ball managed to form a beautiful spiderweb pattern on here. And the glass has actually stayed in place, stuck to the plastic in the middle. They haven't been able to fly off everywhere.
Benedictus layered glass is so resilient because the lightweight plastic stretches when struck, absorbing any force and offering a tear-resistant barrier.
So it's a pretty simple invention, but it's made the roads a much safer place.
As a result, Benedictus founded a company to produce his laminated safety glass. By 1927, it was so successful, the firm was taken over by Saint-Gobain, one of the giants of the glass industry.
Today, Saint-Gobain is one of the largest global producers of glass, and they supply their products for 1 in 2 cars in Europe and 1 in 5 cars throughout the world. Benedictus's chance discovery really revolutionised the car industry and undoubtedly saved millions of lives in the process.
Engineers at Tokyo Skytree take Benedictus's ingenious glass to tackle Tokyo's typhoons.
This is a very tall tower, so the wind is very strong here. If you look at the building down there, the wind pressure here is almost double.
With 2 360-degree observatories and one of the highest skywalks in the world incorporating a glazed floor, each of Skytree's 1,027 panels of glass have to be super strong.
We are in the 450-meter level. Today we are in the cloud. And these are the glass panels.
Installed from the inside and integrated into steel curtain wall framing, this state-of-the-art laminated glass can withstand winds in excess of a mind-blowing 100 meters per second.
These glass panels are with the 2 layers of double-strength glass pane. In between it is this polymer membrane. It is called the layered glass. It is super strong to withstand a strong wind.
Even if the most powerful typhoon came, this system is very safe.
Tokyo Skytree Temple Galleria.
And thanks to Benedictus, in the unlikely event the glass does shatter, it will remain in place, allowing around 4.5 million people a year to safely visit one of the greatest vantage points on the planet.
I always come back here and see people enjoying the great view, and that makes me very happy. And I myself is very the exciting moment to look down the city.
Conceived in 2006, this audacious architectural marvel was constructed in under 4 years, the result of brilliant planning and testing by thousands of engineers.
This is the first time for Japanese to design such a high tower. It is very proud for me to work on this project.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have written a new chapter in high-rise design.
Since the very beginning of the civilization, taller structure has always been a dream of human beings. So constructing world's tallest tower is one of the most exciting and challenging jobs that any engineers can engage.
They have succeeded in making the impossible possible.
Tokyo Skytree is a striking landmark. It's really a combination of state-of-the-art Japanese construction technology and also the very old Japanese wisdom of creating very tall tower.